What does this, what's he trying to show you? I will break my same input into, ma'am, read. I'm going to decompose my input to scale, phase shifted, complex exponential. So then you'll be wondering, why in the world would you want to break, these four guys into complex exponential? Complex exponential is very complicated, right? Something rotating and then, yeah. But this operation has a name. His name? Fourier series, Fourier transform. So you all done Fourier series and Fourier transform? Yes? Yes. So last time, right, he gave you an equation, my x, and then ask you to decompose. He's asking you to break the signal into complex exponential. Can? When he breaks into complex exponential, all these guys add up, must still be equal to him, just like the top guy, okay? So whether you do it this way, or you do it by breaking it into impulses, the result, xn, is the same. Here we understood why they want to break into impulses, because I could use the impulse and then see the impulse response for every sum, scale and delay. Why would I in the world want to do this? Why would I want to bother breaking my signal into different complex exponential of different frequency? Why? Guess, guys. Try to guess. There's something going to happen when I fire a complex exponential into an LTI system. Okay? And it's here. This is CNX, okay? So you all can go and find CNX. The name is called an eigenfunction. This is an LTI system in continuous time. So far, okay? This H is just like a LTI, but for continuous time. I am firing f of t, some function, okay, into a linear time invariant system. For example, out comes f of t again, multiplied by a complex number. So if let's say this complex number is 3, what did the system do to this function? So scale by 3. Okay? If this is lambda is 3 plus j2, so what did he just do to f of t? 3 plus j2. Yeah? Yes, he will create an amplitude change and a phase shift change. Yeah? If f of t is a sinusoid, later on you'll see. Okay? But the take-home message is this. An eigenfunction is very nice. When I send an eigenfunction into an LTI system, out comes the same signal, scale and shifted by time, phase shift. Okay? And then later on, we'll go and prove to you that E omega t, yeah, S of t, E omega t, the rotating phasor, the complex exponential, as you send, pump into the system, out will only come the same guy. So you send one complex exponential of one frequency, out comes the same complex exponential of the same frequency, except, sir? Except? Correct. Again, the same. We amplify or attenuate and we'll shift some phase shift. That's all. Okay? So now you say, if such a beast, such a complex, such a beast, the beast is called eigenfunction exists, right? Then why do I, now maybe you understand why do I do this. Okay, let's see. My very complicated signal is broken down into DC, omega 1, omega 2, omega 3, yeah? Of all different complex exponential, okay? Since the complex exponential sent across is the same complex exponential, right? Same frequency, but scale and phase shifted, I can characterize him. So in this example, omega k is sent, so the original value is some amplitude of this complex exponential, some phase shift of this complex exponential, okay? After I send to him, he is multiplied by B. Oh, this guy introduced BK. He also introduced VK, okay? So at every frequency, he will introduce a different gain and a different phase shift. Across what? All frequency, okay? Across all omega. So what does that mean, guys? I've just told you how the system H behaves in terms of frequency. It is called the frequency response. Up there, I send an impulse. Out comes the impulse response. Here, I send different frequency. Out comes the frequency response. How the system will behave at different frequency. Can you see? So it's very clever, huh? It took them hundreds of years to figure this out. Very clever. Now I can look and I say, as I send my signal in, if the signal looks very complicated, never mind, let's forget about it. Let's look at it in frequency. And then at this frequency, I know, oh, it's going to go up or go down, become louder or smaller, okay, as it passes through the system.